let's take a closer look at filtering. And so as we described in the previous video, filtering is the same thing that you've seen in previous classes where we're blocking some undesired signal, in this case corresponding to our electromagnetic interference, while still passing our power or our signal that we want to be going through. And so there's a couple different reasons that our design for these filters can be difficult. So design can be difficult because one, in some applications, our source and load impedances have a wide range. So source and load impedances can have a wide range. And so this is one example of where this is true would be AC power lines. And so another reason that our filter design can sometimes be difficult is we can have either common mode or differential mode EMI. So can have our common mode. And so this is the same idea that we looked at when we were talking about common mode rejection ratio for op amps in a previous class. So common mode or differential mode electromagnetic interference. So in order to take a closer look at this idea of common mode or differential mode, while also kind of keeping in mind this application of AC power lines, let's look at a circuit that is one phase of an AC power line circuit. So on the right over here we have sort of our three wires. We have our hot, which is our typically going to be black, our neutral, which is typically going to be white, and then our ground, which is usually going to be green or bare copper. And so we can see sort of two situations. We can either have this common mode, which is common between both our hot and neutral, or we can have differential mode voltage, which is between our hot and neutral. And so if we only have common mode, so if we only have some common mode EMI, so I'm just going to put CM for, let's do our VCM. So if we only have VCM EMI, and keep in mind this isn't necessarily our desired source, these sources just represent our EMI. So if we only have the common mode, what we get is that our VHG, our hot to ground, and our V neutral ground, the EMI in both of those is going to equal to our common mode EMI. Now if we also have the differential mode, so let's say we add our differential mode into the mix, so we get VDM, what we have is we can see that our hot to neutral is going to equal our differential mode voltage. So our V hot to neutral is going to equal that differential mode voltage. And if we wanted to talk about our hot to ground, for instance, so let's say we wanted hot to ground, we can see that's going to be any common mode that's present plus this VDM over 2, whereas our neutral to ground would be our common mode minus this VDM over 2. And so again, this is the same basic idea that we looked at when we were talking about common mode rejection ratio for operational amplifiers. Just slightly different application here, obviously. So our neutral to ground would be that common mode minus the differential mode over 2. Okay, so without going into a whole lot of details, let's look at a circuit that we could use to filter our EMI in an AC power line. So a circuit for filtering EMI from AC power line. And so we want to be able to filter both our common mode EMI as well as our differential mode EMI. So let's take a look at this circuit here. So let me move that over to the middle a little bit. But basically what we can see is we have several components. Some are going to be targeted towards the common mode and some towards the differential mode. So our capacitors C1 and C2, for instance, are connecting together our hot and neutral lines, and again, connecting together for frequencies at a certain point, because again, remember for low frequencies, our capacitor will look like an open circuit. As frequencies get higher, the impedance will be dropping. So we can say though that the C1 and C2, since they're connecting hot and neutral, that is going to be reducing our differential mode EMI. So C1 and C2 are working to reduce our differential mode EMI. So then coming back up here, we can say, well, if we have some common mode EMI that's present on both our hot and neutral, the C1 and C2 wouldn't really be helping because it's already on both of those. But that's where these capacitors C3 and C4 come in. So we have a path from each of our hot and neutral lines through the capacitor and then to our ground. So our capacitors C3 and C4 are helping to reduce our common mode EMI. So C3 and C4 are reducing our common mode EMI. So then we only have a couple other components that we haven't talked about. Right here in the middle, we have these two coupled inductors, L1 and L2, and essentially this is another way to reduce our common mode EMI by presenting a really large impedance for higher frequency signals. So we can say those coupled L1 and L2 inductors are also reducing our common mode EMI by presenting a high impedance. The last component up here is something that I've forgotten to draw, or maybe I erased it on accident and didn't notice, but that's just a resistor here, R. And so what this resistor R is doing is it's not necessarily helping to reduce our common mode or differential mode, but it's allowing a path for discharge if one of these capacitors is still charged up and we get disconnected from our AC power line. So we basically get disconnected from that ground connection. So our R is basically allowing or providing, is a better way to say that, a discharge path if any of those capacitors are highly charged up when this filter gets removed from our AC power line. And so this type of filter is typically going to be evaluated by something called an insertion loss. So let's just say our filter evaluated, or we could also say it's a metric used to describe our filter performance. But that evaluation method is something called the insertion loss. And so as the name suggests, what it's doing is it's saying how much loss do we have by transmitting through this filter. So let's say how much loss through our filter circuit above, for instance. And so what we would want is we would want to have a high insertion loss for the frequency range where our EMI is. So let's just say we want high insertion loss for frequency where our EMI occurs. And ideally, we wouldn't want to be sort of reducing or decreasing our signal at other frequencies, but at that frequency where our EMI was, we want our insertion loss to be as high as possible. And so in the following videos, we're going to take a look at our other methods for reducing EMI, and that is our grounding and our shielding.